So welcome back after lunch. Let's now move on. Now that we've done some of the hard work, learning some of the tools, let's now start looking at what was classically considered to be the the model of arbitrarily varying channels, which was these adversarial models, but with common randomness. Okay, so classically people thought of models where Alice wants to communicate with Bob, but there's a key between the encoder and the decoder, and typically they didn't care about the size of the key. Like at least the early literature, when you start looking at this, they basically said, okay, adversaries are hard, how can we simplify the problem so we can still say something non-trivial? And then they said, okay, what if there's common randomness? Let's not worry about how large that key size is, let's try to prove results. And to a large degree that program was quite successful, like under many different metrics: average, maximum, average probability of error, maximum probability of error, state constraints, no state constraints, input constraints, no input constraints, all that jazz. They were able to characterize the capacity. There's wonderful work by Al-Swedi, Chizar, Narayanan. There's a nice survey paper by Lapidoth and Narayanan, and this was quite nice. I'll try to focus again, hone in on a specific example to do with the erasure channel today, but this is true in much larger generality. And again, I would encourage you to look at the survey by Lapidoth and Narayanan. In one particular manner, I will focus on something more, maybe a little bit stronger, which will be, I will focus a little bit on how much common randomness is needed. It will turn out not too much. Like amount of common randomness that scales logarithmically in the block length is enough. So if you have n channel users, then log n bits of common randomness, even explicitly, let's say 4 log n bits of common randomness will be enough. Okay, so it's not too much, and you can imagine that this might be useful, right? You could imagine then having multiple blocks of communication where you start off with a small amount of common randomness, then you bootstrap and then share it and so on, right? So that's one potential use. But again, I would view this as maybe not a model of primary interest, even though this is what was classically the first arbitrary varying channel models were under this thing. But again, as a signpost towards what is possible, what is not possible for other types of ABCs, because what can you do once common randomness is available is one of the first things you should try if you're trying to characterize the capacity of adversarial channels. You should try list decoding if that's possible. You should try common randomness if that's possible. And for example, Marco and I were just chatting earlier about non-memoryless channels like deletion channels. So for example, list decoding for deletion channels, not clear even with adversarial things, but that would be one of the first things to potentially try, and what happens when you have common randomness and so on. So okay, so in this case, so the channel model, as we just said, it's basically just like an omniscient adversary, except the encoder and the decoder are allowed to share some common randomness that the adversary James does not know. This key is unknown. And let's also be explicit. So the adversary knows the code word being transmitted. He also knows the encoder. He also knows the message. So he really knows quite a lot, right? But it's going to be critical that the message to code word mapping not be one-to-one. So for the same message and the same output code word, there are potentially many different keys that could have been used to generate this particular M to X mapping, and that will be somehow critical. Okay, so that will be what we'll be using over here. Okay, so again, just specifically for the erasure model, if you have an adversarial erasure channel, then the capacity under common randomness is 1 minus p, and 4 log n bits of common randomness is sufficient. And in this specific case, because it's an erasure channel, then in fact you even have computationally efficient encoding and decoding just for this case. Not necessarily true in other models. Like for example, if this is a bit flip model, then it would not be computationally efficient. And the underlying reason for this is really, as we'll see, because one of the critical steps, which is list decoding, is computationally efficient for the erasure channel, but not necessarily for other channels. Okay, so we'll see this a little bit later. Okay, so in this case, so how do you prove it? And it's a nice, cute black box reduction. There are many different proofs. Here's one that I particularly like. So what does the encoder really do? So it says that I'm going to So I'm going to take the message that I want to send, and then take a okay. So first of all, the key you can think of as being composed of two subkeys, k1 and k2. Okay, so and in particular, the encoder first takes the message and takes a hash of the message with respect to some function of this key, which I'll specify later. It will append that hash to this message, and then from that point onwards, that message comma hash pair will be the meta message for a list decodable code. Okay, so it will pass the message comma hash pair as a m prime to a list decodable encoder decoder pair. Okay, so that's the
one possible message in that list of things where the common key is.
Indeed. So that will be the whole bottom line. You'll want to show that with high probability, because this will be a high probability guarantee. You'll want to show that with high probability over the adversarial actions. Well, okay, we'll make that statement more carefully. But the adversary can do any action he wants, but regardless of the action he does, over the unknown randomness to him, with high probability over this key, there'll be only one key that matches. So so let's be a little bit more specific. So it's the first thing after lunch. So let's go slowly. Let's try to make sure that people are following along. At least one proof in each session, should be a goal, right? So let's say we have 4 log n bits of common randomness, right? So let's say this first subkey is 2 log n bits, the second subkey is 2 log n bits, right? So we'll be operating over fields of size 2 log n bits, that is 2 to the 2 log n, that is n square. So the field size will be n square. Okay, so each of this k1, k2 are from fields of size n square. By the way, these 2's and so on don't really matter. I'm just trying to be very explicit over here, right? Like you could have 3 log n, 1.5 log n, and so on, but let's just be explicit. Okay, so now partition this message so that it's basically, you can view the message, which is a binary vector. You can also view it as being an element of the same or as being a vector over the same field. So partition it into message symbols over that same field. So now you'll have n over 2 log n such symbols, right? So it'll be slightly sublinear number of finite field elements. And now the hash you'll use will be, it shouldn't be too surprising, it'll be sort of a polynomial hash that will be similar to the sort of Reed-Solomon code encoding things that you do and so on, right? So basically you'll take these message symbols and multiply them with powers of k1. So k1 to the power of I, sum these up, and then mask it with k2. So add k2 to it, okay? So this hash that you're generating, the hash of the message with respect to the keys, is take a polynomial, so define a polynomial using coefficients from the message, evaluated at k1 with the k2 masking, so to speak. You're adding k2 to it, okay? And then makes the proof cleaner. So yeah, don't worry about it. It's whatever. So the effective transmitted code word will then be again the encoding of the message and the hash. And you do this, and this will be a list decodable code, which, as we've noticed, you can use a random code, you can use a linear code, and if you want computational efficiency, you probably want to use a linear list decodable code over here. Okay. All right. So now as Krishnamurthy said, what do you want to do for the decoder? Well, the decoder first of all outputs a list size, a list, and then checks the hash function. So for all the possible key, for the specific key values, it checks which of the elements in the list satisfies the hash, hopefully only one, and if so, output that. And then the question becomes, what is the probability of error? What is the probability over adversarial actions that more than one satisfy this thing, right? And that's where the analysis comes in. But what I'm going to state over here will actually be independent of the channel. It's sort of a black box reduction. So as long as you have a list decodable code in the middle, then you could always do this disambiguation step on the outer side. Okay. So now we'll actually even strengthen the adversary James in a subtle way, which will just make our proof a little bit easier. We'll say that James can. We'll forget the channel in the middle. We'll say James can play this game. He can always give Bob any list he wants, with the caveat that this list has to contain the encoding of the true message. Okay. So notice that in reality he can't actually do this, right? He has to do this in a certain manner by erasing a few bits, and that will instantiate a list, and not all possible lists are possible, right? But we'll give him the power to actually choose anything he wants to put in the list, as long as that list has the truly instantiated, like the truly transmitted code word within it. Okay, it will just make the analysis a little bit easier. And oh right, and the size of the list is at most size 1 over epsilon. So so the true message will of course always pass the disambiguation test. The question is, what's the probability that something else will? And yeah, if there's something else that's consistent, then you have a problem. Now, here's an important fact. So let's, it's actually a little bit subtle. I mean, can be a little bit confusing. So let's just go a little bit slowly here. So the point is, given what the adversary sees, and we'll be explicit about it shortly, the distribution of the adversary, the distribution of K1, just K1, not K2, not K1, K2, but just K1 from the adversary's point of view is going to be uniform. Okay. So what does the adversary see? The adversary knows the encoding scheme, he knows the message, he knows the hash, he knows the he knows the message, he knows the code word. Therefore, potentially he can decode, potentially knows the hash, he knows all of these things, right? But a priori he doesn't know K1, K2. So based on his view, based on his view of M, H, X, what can he compute about K1, K2? We really should be careful about this, right? So the point is, since the hash is equal to K2 plus this polynomial of K1 times the message, he knows the message, right? A priori he doesn't know this, but he knows H. So K2 and K1 are potentially unknown. So the point is, for any K1 that Alice could have chosen, there is always going to be a unique K2 that will make this equation be satisfied, right? So if the adversary sees the message and the hash, the encoding X doesn't convey any extra information. So if he sees the message and the hash, for any value of K2, there's a unique value of K1 which makes this equation be satisfied. Therefore, K1 is uniformly distributed with respect to the adversary's view, with respect to what he's seeing, right? So what is that saying? It's saying that in this polynomial, which is of degree at most n, actually slightly sublinear in n, there are this is a sublinear degree polynomial, but K1 is uniformly distributed. It's as if that of the potentially n square possible values that K1 could take, there are at most n roots to this polynomial, and the adversary really has to try to hit that, right? And this will happen with small probability. That's what we leverage. Okay, I'm just giving you a sneak preview. So let's go to the next slide. So now what do we say? Okay, so this is what's happening with the true message and the hash, right? It satisfies this equation. Let's say that adversary presents some fake hash, some fake message, okay? And the fake message has to differ from the true message, otherwise the adversary won't succeed. So this is some other candidate thing that he puts on the list to try to confuse Bob, right? So if these two both have to be true, then you can always subtract these two out from each other, and you'll end up with, yeah, it's not on the slide, but you'll end up with h minus h prime is equal to, the K2s will cancel out, and the K1 i's times the m minus m primes, right? So you'll have a polynomial in K1 times the m minus m primes. So basically it will say that the adversary, let me just write it out so it will be explicit. So it will basically say that this equation has to be satisfied. H minus h prime is equal to summation I goes from 1 to n over 2 log n K1 to the power of I mi, right? This minus m prime I. This equation has to be satisfied. So it's like saying this polynomial where the adversary gets to control this, like he knows this and he can choose this, so he gets to control this, he gets to control this, but he doesn't know what K1 is. It's uniformly distributed from his point of view. So it's like saying he knows the polynomial, but I mean he gets to control the polynomial, but he doesn't know what root to aim for, right? The true root K1 is uniformly distributed over a field of size n square, but this polynomial can have at most n roots, it's slightly less than n roots. So the probability that he will succeed in confusing these two is going to be order, well, by the short zipper lemma, it will be, or even just counting roots, it will be like order n over n square, right? So this is order 1 over n. And then you have to take a union bound over all the elements in the list, but that's just a constant number of elements in the list, and therefore this goes through. Right? So that's a proof. It's a simple black box proof and works for any ABC. Yeah? All right. So yeah, this is basically what I've already just said. Then, yeah, so just to highlight, again, a small number of bits of common randomness was enough, and the encoder complexity was order n square, and so on. Yeah, so the converse, the proof follows directly in the sense that, well, you can't hope for more than 1 minus p. Potentially, slightly more surprisingly, and I don't have a slide for that, and it's a little bit more of a counting argument, so I'm not going to attempt it, but it also turns out that not only do order log n bits of common randomness suffice, but they're also actually necessary. If you want to get to the list decoding capacity, then sub-logarithmic number of bits of common randomness are not enough. You need logarithmic bits. This is due to work by Langberg, the Fox paper, and so on. I misspoke. If you want to get to p minus, like if you want to get to c1, well, I mean, capacity is defined as a limit, right? So basically, if you want to get 1 minus p minus epsilon for a vanishing epsilon, then you log n bits are necessary and sufficient. Log n bits of capacity are necessary and sufficient.
Let's say if you want 1 minus 2p, then can you get a
much improved in the bits of common.
Capacity, but you want to keep some
So if you go all the way down to the GV bound, for example, then you don't need any common randomness, right? So in between, that's a fascinating question. There's been recent work by Polyansky, where and also Brinovsky, less like whatever. So there they look at list decoding with explicit numbers of list sizes. Like what if you wanted a list size of 3, 5, 7? Odd numbers for some reason are easier to characterize than even numbers, and they have sort of bounds which are in between the GV bound and the LP, well, in between the GV bound and the list decoding bound, so they can get things like that. Okay. But the even subtler question of, well, what if you wanted list size of 7 and log n bits of common randomness? That I don't know, and that's complicated. Okay. All right, I think that's all I wanted to say about this model. Now let's move on to another model. So channels with feedback. So in this case, okay, so for general stochastic discrete membrane channels, feedback, as we know classically from our information theory classes, feedback doesn't improve capacity, but it gives better performance. You can get smaller error exponents. You can have simpler schemes and all of that, right? So I'm not going to reprise that. But we are interested in what happens in adversarial channels. Yeah, so suppose we focus on the channel model we've been using as a benchmark so far, the erasure channel. Then the forward channel James can erase up to NP bits, and in the reverse channel he can observe but not corrupt in any manner everything on the feedback channel. And if this is the model we start off with, it's actually quite straightforward. Okay, if you think about it even a little bit, it should be clear that you can get a capacity of 1 minus p exactly, not even any asymptotics, because in this specific case the strategy is clear, right? Whenever James erases a bit in the forward channel, Bob sees, Alice sees that it's been erased, she just retransmits, right? So this scheme would get you to 1 minus p, right? So this is maybe not quite so interesting. Let me actually, it's not in the slides, but let me also tell you, just because it's a fascinating classical result, which again I'm not sure I fully understand, would not be able to do justice to the presentation certainly, but for the bit flip case, that's a whole other beast. And if we had a similar channel where James can flip up to NP bits, and then on the reverse channel is entirely clean and nothing is corrupted. So what is the capacity over there? It's a fascinating capacity region. There's a classical work by Burlekamp in the 60s. In fact, this was part of his PhD thesis, where the capacity region is sketched as follows. It's related to Ulam's problem, 20 questions with liars, and so on. And there's a more recent follow-up work by his student, Desjardins. Anyway, so over there, the capacity region for the binary case happens to look like this. It's like do. And what's happening over here? There's a two-part curve. Up to here, it's basically the 1 minus HP curve. This is the p-axis. This is the rate axis. Over here you have 1. This point is 1/3. From here to here, it's a straight line. and this line is basically the tangent to the 1 minus HP curve over here. Okay, so very weird curve, right? But actually, we'll see something like this later on as well when we come to the causal channels. The sort of two-part behavior to the channel capacity shows up over there as well, because what ends up happening is that in the very low noise regime, the adversary has different choices at his disposal. He could just behave like random noise, or he could try to do something more mindful, taking into account the code structure, the strategies, and so on. But really, in the very low noise regime, since the slope of the entropy function is so steep, he gets so much out of just behaving like random noise that none of the adversarial strategies that we know of, or indeed that can be known of because it's a capacity characterization, really beat that. But once the slope flattens out, once it becomes like this, then there are certain attacks, and related, for example, to the Plotkin bound and other bounds that we'll see again in the causal case. Over there, those start dominating. Those have a higher hit on the higher penalty on the rate, and therefore the adversary wants to start sort of time sharing between these two strategies and so on. That's from the converse point of view. To argue that this is indeed achievable requires more sophistication and so on. And again, we'll see an explicit example of this when we come to causal adversaries. But I did want to point out, before I move on to other models in the erasure case, that even the feedback case is quite intricate, even with something as simple as bit flip adversaries. Okay, and the result over here is due to Bullicamp, and there's some nice combinatorial ideas here. Okay, so coming back, if the adversary can erase up to NP bits, but it's completely noiseless feedback, then it's quite straightforward. Alice can just repeat every bit that was erased, and therefore you get 1 minus p times n, right? Okay, so what if we restrict the problem somewhat more? Yeah, so this is just retransmission. So what if the reverse channel is rate limited, which is to say something like for every 100 bits forward, you can transmit 1 bit back. For every 1,000 bits forward, you can transmit 1 bit back, and so on. So, so something like that. But it's rate limited, but it's still noiseless. Okay, so the adversary isn't allowed to corrupt things here. And in all honesty, I'm talking about this channel just because we have something concrete about this channel. There could be other problems. There could be problems where, like, okay, the 1 bit forward, 1 bit back, but the adversary could corrupt this as well. And something less is, something is known over there, something non-trivial is known, but a capacity characterization is open. So again, there are multiple variants of this problem. Just for today's talk, to keep it clean and simple, I'm going to focus on this particular version where it's rate limited but noiseless. Okay, and there's work in the computer science literature, coding for interactive communication, where you have two-way channels and noise is allowed on both, adversarial noise and so on, and then there are very nice schemes over there which give you something. Okay, all right, so so in this case, yeah, again, just to be explicit, it's something like this. So I'm just going to focus on the following. Again, the actual numbers don't matter quite so much, but let's pretend that it's sort of, it's a round-based scheme where Alice is allowed to transmit square root of n bits in the first round. Bob is allowed to respond with, let's say, log n bits. Log n is much smaller than square root of n. Then Alice transmits square root of n more bits. Bob can respond with log n bits, and so on. So the forward rate, like there'll be square root of n rounds. So overall, there'll be n forward bits, but there'll only be square root of n log n reverse bits. So really, the reverse rate is vanishing. You're transmitting very little in the reverse direction than you're transmitting in the forward direction. Okay, and again, the square root of n log n don't really matter that much. There's a lot of flexibility here. Basically, the punchline is the reverse rate can be vanishing compared to the forward rate noiselessly, and that's the model I'm going to focus on. Okay, just for clarity. By the way, this is unpublished work, so this would be part of the things that I prefer not to be on the, not to be publicly broadcast, at least yet. We're writing it up. So, so in this case, yeah, we're just going to focus on this fixed peaking order, square root of n log n, square root of n log n always, and it'll be a protocol. There's some notation to go with it, but I think you already understand. I'm going to skip this. So, so basically, you can show that in this case, you can still get 1 minus p minus epsilon. Epsilon goes to 0 rate, even when delta f also goes to 0. Okay, so feedback rate goes to 0. And in fact, this scheme will also be computationally efficient. It will also be order, poly n computation, encoding complexity, decoding complexity. Okay. Yeah, so in this case, notice feedback does improve the capacity in the adversarial regime, right? Even vanishing feedback. Okay. So the converse is clearly 1 minus p. You can't hope to do more than 1 minus p. James could always erase p times n bits. So here's how an achievability would go. You could say that Alice does the following. So first of all, again, list decoding as a primitive is quite useful. So let's do that. Let's choose a random linear code, which will be list decodable with high probability. Okay. And now, having generated this list decodable code which would transmit, code words of length n over so if the message rate is 1 minus p, so there are n times 1 minus p roughly message bits, and there are n code word bits. So this is how you're going to choose a list decodable code. This G is known to everyone, Alice, Bob, and James. There's nothing hidden over here. Okay. And now you're going to use this protocol. Now what does Alice do? It will be somehow a two-stage protocol. So initially, Alice will just be transmitting square root of n successive bits of the encoding of this random linear code. Okay. So she'll use this random linear code, transmit the first square root of n bits of the corresponding code word that she would have transmitted if with the encoding. Then Bob will feedback something, and actually in the first stage his feedback doesn't really matter, because square root of n bits Bob can't possibly hope to decode. Alice knows this, right? So she'll just ignore it, right? Square root of n more bits, Bob still can't decode, and so on. Really, what will Bob say initially? He'll just keep saying can't decode, can't decode, can't decode, can't decode. So that's just a single bit, right? 0 or 1. Can I decode yet? Can I list decode yet? Can I not list decode yet? Okay, that's just a single bit. And initially, of course, he can't list decode yet. He cannot hope to list decode until, well, at least order square root of n rounds. So initially, his feedback will not really be very useful. Okay. Now, at a certain point in time, Bob will be able to list decode, right? He'll be able to list decode when the number of unerased bits to him is approximately equal to the number of message bits, right? Because that's how list decoding works for erasures. When the number of unerased bits that you observe is roughly up to this epsilon fudge factors equal to the number of message bits, then you can hope to list decode. And Bob knows erasures. That's one of the nice clean things about erasure channels. So he knows he can list decode. And then he tells Alice, using his feedback, he has log n bits of feedback. He actually needs just 1 bit of feedback, saying, aha, now I can list decode. Okay. So at this point, Alice and Bob both know that Bob can list decode. Okay. So then we segue to the second part of this protocol, the second stage of this protocol, which will be a little bit more mindful. Okay. So what would the second stage of this protocol do? Yeah. So in the second stage, now Bob can list decode. Alice doesn't know what Bob's list is, right? She just knows that Bob can list decode, but she doesn't know whether erasures have happened so far to Bob. So she doesn't know what Bob's list is. However, Bob can use the log n bits of feedback to give some insight as to what his confusion is. Okay? So if he has some confusion at all, I think there's a figure to do with this. No, maybe not. So if he has any confusion at all, then at this point he's list decoded down to maybe order 1 over epsilon size, right? Some constant list size, and there are order 1 over epsilon code words, each of length n, that could have been transmitted by Alice, right? And he just doesn't know whether okay. So now these code words are different. That means that there has to be some index I where at least one of these code words is a 1 and one of the code words is a 0, right? There has to be some confusion. They can't all be identical everywhere. So they must differ in at least some index. So he picks any such index where he has at least some confusion.
At that point, let's say the pathological case, there is only list that point is one particular one particular code word. Why is that wrong?
I'm sorry, repeat?
I mean, you say it's a list, has to be of size 1 over epsilon.
Mm-hmm.
What can be a pathological case where the list essentially is degenerated to just one?
Okay, so if Bob's list is unique, then he's already uniquely decoded.
Not necessarily, right? You could have uniquely decoded wrongly.
List decoding has a following guarantee that the correct one is always there, right? So at this point, there's a list of no larger than, just to repeat the question, So the question was, well, what if the list size is just unique? And in this case, there's no issue at all, because then Bob can uniquely decode, right? So, but if it's not unique, then there's at least 2, maybe 3, 4, 5 different code words. They're different, so there's at least one index where at least 2 code words are different. And Bob just uses the log n bits he has at his disposal in the reverse round to describe this index I. Okay? So he says to Alice, tell me what index I was. Was it a 0 or a 1? Okay? And now Alice will use the remainder of like the next round to just repeat index I. If it's a 0, she'll send square root of n zeros. If it's a 1, she'll send square root of n ones. Okay? She'll just be tremendously wasteful. She'll try to send it. Okay? Now notice what happens. Either James erases his entire chunk, in which case Bob is still confused about this index, in which case he'll say, well, tell me I again, right? Or James at least lets one of the bits slide through, in which case immediately one of the code words is removed from this list, right? So then it just becomes a counting argument. How many bits does James have left at his disposal to erase versus how many rounds of successful transmission do you need to get through? And it's actually a quite straightforward counting calculation. You can convince yourself without too much effort that, okay, James just can't screw with you, right? Eventually he'll have to let Bob be able to figure out what's happening. So that's really the protocol. Okay, it's not too complicated. So, so just to summarize, what have we learned over here? Let me just see if there's, yeah, it's basically just this. So basically, we can get to the channel capacity 1 minus p with vanishing feedback, computationally efficient scheme. Again, because we had computationally efficient list decoding. If we did not have computationally efficient list decoding, would not have been possible. It's actually 0 error in this case, which is quite nice. And feedback does improve the capacity, right? So that's nice. Yeah, so we do not currently have versions of this for bit flip adversaries, and if someone's looking for a problem, you know, that's fascinating. I have ideas on how to proceed, but there are nasty little protocol level issues which one has to deal with. But bit flip, deletion channel, things like that would be fascinating. Okay. All right. Channels with myopic adversaries. So keeping an eye on time, we have like 25 minutes. For this, I'd actually like to segue to different. I'm sorry? No, that was just a mistaken click. What I am going to do is going to go to a different talk. No, not this one. Oh, crap. Yeah. This is yet another symptom of ISIT deadline. So there was something where I couldn't quite, that was maybe a bit too much. Yeah, where I couldn't quite get 2 different files to compile simultaneously because of messy stuff. So we have a different file here. Okay. Yeah. Actually, I'm jumping ahead just because I'm like, oh, I have to get through it. But really, maybe we do have a few minutes for questions. Any questions about the feedback case? Okay, I should have asked them. But okay, let's move on to this model, and we'll make sure that there's time for questions later on. This is a model which I find quite fascinating. We've done quite a lot of work in this. We may not be able to finish before the break, so this will probably be split across the 2 sides of the break. Okay. So, so the model over here is Alice has a message, she encodes it into a code word X. This is then broadcast, and first the adversary gets to see a noisy version of this transmission non-causally. So he gets to see the entire transmission X through a noisy transmission channel, and then gets to decide how to attack. So maybe erase or flip bits or something like that. Okay. And for the purposes of the current talk, I'm going to focus on, instead of the bit binary erasure channel, I'm going to focus on the binary symmetric channel or the bit flip channel. Okay. So think of this being like a bit flip channel, like a random noise bit flip channel. So maybe the probability of a bit flip in this direction is q, and then based on a roughly fraction q bit flip channel model over here, the adversary gets to see this, and then he gets to flip up to q times n bits over here, up to p times n bits over here. Okay, yeah, these 2 parameters will be important. So let's just make sure we remember which is which. P corresponds to the noise on the main channel, right? So this is a adversarial bit flip P channel. Q corresponds to the random noise on the channel towards James. So that's the noise coming towards him. Okay. And if you think about it, this as a here I'm focusing on the bit flip case, but the general myopic channel is actually quite general, right? Like for example, when yes, typo. I was about to say that. So when Q is a half, then this is a perfectly noisy channel. Then it's as if James is not seeing anything at all, right? When Q is 0 or 1, then it's the omniscient channel, right? But there are intermediate problems of interest where Q is, and here we'll say when Q is less than P, that is, or let's start with this, when Q is larger than P, that is the random noise towards James is larger than the noise he can impose on the channel, and implicitly both of these are less than a half. So if the channel to James is noisier, the random channel to James is noisier than the adversarial channel he can impose towards Alice, then roughly speaking, and we'll formalize this more later, then roughly speaking, this is what we'll call a sufficiently myopic channel. Okay, and this will actually turn out to be easy. Well, easy is the wrong word, but it will turn out to be possible to characterize the capacity tightly in this region. Okay, whereas the insufficiently myopic regime, if you think about it, is closer to the omniscient channel, right? So in this case, the capacity will be trickier to characterize. Like in fact, we don't have a characterization. We have some non-trivial ideas. So, but as you can imagine, in the limit, it starts getting to this truly hard problem. So we cannot hope, or at least I do not really hope to characterize it fully. But at least we begin to get some insight into the structure of the types of good attacks, good achievabilities, and so on. Yeah. Okay. So, okay. So moving on. Just a break. Okay. Yeah, one other thing I'd like to highlight. So in this case, we will characterize the myopic capacity under deterministic encoding, which is good, but only under average error. Okay. Notice, remember we set out our desiderata in the beginning. We said we really would like to characterize the capacity under deterministic encoding under maximum probability of error, right? That's the strongest thing. We cannot yet do that. We can only do it under average. There's some reason to believe that there are strong bottlenecks towards characterizing it under maximum error, but that's a sort of technical note. Okay. Okay. All right. So yeah, like I just said, the theorem that I'll try to prove really, or at least sketch a decent version of the proof in the next whatever time, is going to be that the capacity is 1 minus HP. It's the capacity. It's the same as the as the capacity of the Shannon channel, or the list decoding capacity of the binary symmetric of the adversarial bit flip channel. I'll try to prove it as it's equal to this, and it's clearly, James can always just behave like random bit flips. So clearly you can't hope to do better than this, but the challenging part is indeed the achievability, how to prove the achievability. In fact, even the codes that achieve this will just be random Shannon codes. So you'll just choose a rate of 1 minus HP minus epsilon, choose a random code, and that's the encoder. The decoder is going to choose the minimum distance code word. It's really just that. The main challenge is proving that this works, okay? Because now the adversary gets to see something quite tightly correlated with what was transmitted. He has a relatively small amount of uncertainty, so you really have to look at what's happening within the set. Okay, so that's where the challenge will be. So, right. So as I said, codebook design is just random. You choose 2 to the n code words uniformly at random from 0 1. Encoding, just transmit that code word. Decoding, choose the nearest code word, and declare an error if there's nothing, whatever. All right. So yes. All right. So the question over there, which I remembered for the first time to repeat before trying to answer it, yeah to me, is why do average and maximum potentially differ over here? Why are they not obviously the same based on our earlier argument? So notice that when we were making our earlier argument, arguing that the average and the maximum probabilities of error have the same capacity, even if we don't know what it is, implicitly we were assuming that it comes down to the balls not intersecting, like the confusion sets not intersecting. Because if they intersected at all, then the adversary would carefully be able to add noise so that you end up in the corresponding region, right? Now, in this myopic case, not obviously doable, right? Because the adversary is getting to see something noisy, right? And he may not know exactly the transmitted code word, right? And therefore, he may not be able to carefully sort of push noise in a certain direction. Okay, it's actually even trickier than that.
Some code words, they want to push it in one way, and
For others in another way, it's actually even trickier than that. I suspect what may end up being the optimizing code book distribution over here, or at least a non-trivial code that would perform better, at least in certain scenarios, than a random code, would be a superposition based stochastic code, by which I mean the following: choose your 2 to the nr messages, and for each message choose a single code word, and then for each of these code words choose a small number of other code words which are close to this, and now transmit one of those uniformly at random. Okay, so there are some reasons for these myopic adversaries to try to transmit a bunch of code words for the same message which are close to each other. And the reason you want to do this is because when James is trying to figure things out, you want it to be possible that even if he can figure out the message, he should not know what the transmitted code word is. Okay, you want something like this, and therefore these sort of more structured, still random but more structured codes may perform better. Okay, now this is probably a way more detailed answer than you want. It's also based on a lot of speculation. We don't actually know how to prove many of these things, but this is indeed one of the questions we're looking at, and I'm happy to chat with you more if you're interested. Okay. All right. So, okay. So coming back to this, so the code design, encoding and decoding is exactly as you would expect in a random code, but the analysis is the tricky part. So let's move quickly onto that. Okay, so first of all, the noise towards James, so there's some random bit flip noise being added towards James. This is again tightly concentrated. It's just the Chernoff bound, right? Because this is random noise, so the Hamming weight of this is pretty close to n times q times 1 plus minus epsilon. So that's tightly concentrated. Okay. Now, what does this allow us to do? So now let's look at it in the following way. So James is seeing this received vector z. He knows that the truly transmitted code word is with pretty high probability somewhere in this shell over here, right? Somewhere within nq times 1 plus minus epsilon. Now, even within this shell, there's some slight variation, right? So actually there are some linear number of shells over here with each with unit thickness, right? So what we'll do is we'll just to make our analysis easier, we'll give James some extra information, okay? And this extra information will be in 2 parts. So firstly, we'll tell him exactly the shell that the true code word is on. So the true code word is this red code word. We won't tell him that this is the truly transmitted code word, but we'll tell him that the Hamming distance between the true code word and what he sees is exactly this value small d. Okay? So why do we do this? It's really just for technical reasons, because now once we condition on this value small d, then every one of these code words on this shell is equally likely to have been transmitted, right? Because it's a bit flip channel. So it'll be easier to analyze. We can just count numbers instead of having to worry about probabilities. Right? I'm sorry?
This flip, it's a binary relation.
So yeah, I've decided to go with the bit flip version because we all like to think in terms of balls. There's a similar argument to be made with graphs, bipartite graphs, and so on for the erasure case. Okay, but again, the underlying geometric objects are different, but it's doable. Okay, and indeed, actually, this result can be generalized again to a fairly large class of AVCs, not all, and I'll try to speak a little bit towards that near the end. Okay, so this is the first sort of information we reveal, which is the exact Hamming distance of how far away the truly transmitted code word is from what's observed. And that's understandable, right? You want to uniformize probabilities. The second thing is potentially a little bit more surprising. Again, it turns out to have just a silly little technical reason at the end. It won't be obvious right now. But we'll just say, we'll even do something maybe surprising. We'll say, okay, there are potentially exponentially many code words over here. We'll actually do that calculation. But we'll reveal to James that the truly transmitted code word is within a set of size at most 2 to the n epsilon within this. Okay, so let me do this a little bit more carefully. So if you think about it, this shell, that shell that I'm drawing over there, this is Z, and this shell is of volume approximately 2 to the n h of q, right? The message rate is 2 to the so therefore the fractional volume is 2 to the n h q over 2 to the n. This is the fraction of the volume of the space occupied by the shell. The message rate is 1 minus hp. That's what we're going to aim for, right? So or minus epsilon if you cancel this out. So this will cancel out with this, and therefore you have 2 to the n times hq minus hp minus epsilon, which okay I'm going to ignore over here. So basically, in expectation, this very large exponential number of potential code words are these yellow code words that lie on the shell, right? So pretty large exponential number, but this oracle will do something even more. He'll reveal to James that actually the truly transmitted code word lies within a subset of size only 2 to the epsilon n out of this 2 to the n h of q minus hp. Okay, so again you're giving him a lot of information, and clearly the more information you give James, even then if you're still robust, then you're doing okay, right? Because code against a stronger James will work against a weaker James. Why are we doing this? You'll hopefully see later. It's a silly little part of the counting argument where just making sure that the numbers are small will make things go through more easily. Okay. All right. So far so good. So James has seen the Z, and now he knows that the truly transmitted code word is within a relatively small but still exponentially large set of size 2 to the epsilon n, each of which is of distance exactly d from what he's seeing. Yeah. Okay. So now, yeah. So this is just saying what I've already said on the board. Okay. So now the error analysis goes in various steps, and we'll see how much I can get through. Well, I'll hopefully try to finish at least this part before the break. Okay. So we'll try to show that the probability of a bad code book. And what is a bad code book? A bad code book will be a code book which has various different sub-events, but we'll try to argue that each of these sub-events happens with probability that's super exponentially small, smaller than 2 to the minus n, so something like 2 to the minus n square or something like that, in small for any fixed z, that is what James has observed, any state vector that James can impose, any d that instantiates. So notice that these are at most exponentially large. There are at most exponentially many s's he can enforce, at most exponentially z's, and at most a linear number of distances, right? So you can take a union bound over these. So what are these bad events that we have to worry about? So the first one is how many code words fall within this shell. Okay. So in expectation you expect something like this, but of course there could be some variation around it. But since the expected value is exponentially large, so the probability of deviation by more than 1 plus minus epsilon is super exponentially small, right? So therefore, that's one of the first things, right? In every shell, are there sufficiently many code words? Yes. Yes, true, with probability super exponentially close to 1, right? And therefore, that's tightly concentrated. Okay, so Oracle partitions the code book with these shells into equal size sets, and then reveals which subset reveals to James which subset the truly transmitted code word falls into. There's a slightly technical point here which I'm going to say briefly. If you don't get it, don't worry about it. This partitioning business, partitioning of the shells into these subsets, happens before transmission, before Alice actually transmits, before the noise instantiates. The reason for this is because we don't want to have to worry about super exponentially many different partitions, which you would have to if you did things in the other way. So you just decide these partitions in advance. There's only exponentially many partitions to worry about, and it all gets done in advance. Okay, so don't worry about it. It's just one of those technical points. Okay. All right. Now, and this is this is maybe the most geometrically important slide in this part of the talk. So let's just make sure we get this, and then the rest will be a little bit of counting arguments and so on. So what are the types of error events that you could have to worry about, right? So, so there are three types of subsets given given James's confusion set. So given the oracle given set that he has. So it could be that once James fixes his attack. So okay, let me start again. So Alice has transmitted some code word. James observes some z, which is at a distance d, and then he chooses to impose a certain attack vector s. Okay, which attack vector? It won't matter which one. We'll take a union bound later. But right now, let's do all of our analysis for a fixed attack vector. So we have fixed this attack vector s, this state vector s that James is using. So for this state vector, there are three different types of subsets of code words which we have to worry about. One of them corresponds to yeah. So one of them, yeah. So let's start with S2. So there are these code words here on the shell, exactly, right? But there's a whole bunch of code words that are not on this shell, and potentially once you translate this, once you translate the truly transmitted code word by S, then something else is going to confuse it. Actually, let me see. I think there's a diagram to do with this coming up. Yeah. So we'll So let's look at this. So from James's point of view, there are 2 to the epsilon n code words over here. He chooses the attack vector s, right? And after translation, what Bob would get, if this was the transmitted code word, if this is the code word that Alice is actually transmitting, this would be what Bob would receive. If this is what she is transmitting, which she actually is, this is what Bob would receive, and so on, right? So the question is, well, if this was what Alice was transmitting, what could Bob be confused with? He could be confused with these 2 other code words. If this is what Alice was transmitting, Bob could be confused with these 3 other code words, and so on, right? So what we have to worry about is, for each of the code words in the oracle given set, under the action S, are there other code words that could confuse Bob? And these other code words, we'll worry about classifying them into 3 different types. Firstly, are these other code words in the oracle given set or not? That's what we'll call S0. Okay? If they're not in the oracle given set, are they still on the same shell? That we'll call S1. And if they're not on that shell at all, we'll call that S2. Okay? Not very intuitive names, but let me just repeat that. So there's a certain oracle given set for James. He does an attack vector S, and then each of these things in the oracle given set translates by S. Now you look at the potential confusing code words for each of these balls and classify them according to whether they're in the oracle given set, not in the oracle given set, but in the shell, or not in the shell at all. And that's S2. Okay? And we'll do our error analysis for each of these 3 types of code words separately. Okay? All right. So yeah. Okay. Yeah, this is going a little bit quickly in these slides, so let's see how much we can do. All right, so I'm going to focus maybe before the break, because this is heavy going. I just want to make sure that that one of these steps gets reasonably classified. So let's do this one. Okay. So there are these 2 to the epsilon n code words within the thing. James has done an attack vector S over here. And now we're going to worry about the error event corresponding to S2. So we're going to start with S2. And remember, S2 corresponds to x primes which are not in the in the shell. Okay, I'm just going to write shell. By the shell, the meaning is clear, right? So now let's say this is the truly transmitted code word. This is what's received, and then there's a ball like this, and then a ball like this, and so on. Now, first of all, and this is what will begin to tell us why we did that whittling down of the oracle given set to size 2 to the n epsilon. So let's first try to come up with something called blob list decoding. Blob list decoding. So what is blob list decoding? So blob list decoding will ask the following question. From James's point of view, you know, an object of interest is this thing that we're calling the blob, which is the union of all of these balls. Bob is actually only seeing a single ball over here, right? But James doesn't know which ball. So from James's point of view, let's just take the union of all of these balls, and let's call that a blob. Okay? Now, what is the volume of this blob? The volume of this blob is basically 2 to the n hp times, well, if you have 2 to the n epsilon by 2, then it would be something like this. Forget the 2 over here. It's basically really, if you forget the epsilon factors, it's really basically 2 to the n hp, right? That's really the volume of this blob. I mean, you have to multiply by 2 to the n epsilon because there are 2 to the n epsilon different such things, but that doesn't really fundamentally change the exponent that much, right? So the volume of this blob is still the same. So now you can ask yourself, over the randomness in the code design, how many code words do you expect to fall within the blob? Okay? And when you do the list decoding argument, the same list decoding argument we did in the previous hour, the expected number of code words will be small, and the probability that there's more than, let's say, n square code words falling within this ball, more than n square code words of type S2 falling within this ball, is super exponentially small. It's smaller than 2 to the minus n square. Okay? So that's why we call this blob list decoding. It's a little bit different than list decoding, right? It's not in a single ball, it's in a union of balls, but the probability of there being more than n square code words falling within this blob is super exponentially small. Okay, so that's very good progress, right? Because now it looks like we now have the following argument, right? There are only maybe n square confusing code words from Bob's point of view, but there are 2 to the epsilon n potential things that could have been transmitted from James's point of view, right? So it looks like, at first sight, it looks like the probability of error, at least due to these types of code words, it looks like the probability of error conditioned on S2 types of code words is less than n square over 2 to the n epsilon, right? Because there are only n square confusing code words, but there are 2 to the n epsilon balls, so, you know, can't be too large, right? Only n square balls would be confused. Unfortunately, this isn't quite true. It's almost true, but it's not quite true. It's not quite true because a bad situation like this could happen, which is these balls could maybe have lots of intersection. So a single confusing code word could confuse many different other code words, right? That could happen. So that's why we need a separate concept called reverse list decoding. We also want to compute a single confusing code word. How many confused code words can result from a single confusing code word? Okay, and at this point, to not confuse you too much more, it really does. I mean, it really just does come down to another list decoding argument. You can also argue that this reverse list decoding thing that we have to worry about is also behaves similarly. You can also argue that a single confusing code word cannot impact too many other truly transmitted code words in the oracle given set. Okay. So overall, there are at most n square times n square confused code words, because there are at most n square confusing code words. Each of these confusing code words can impact at most n square confused code words. So overall, n to the 4 confused code words. Okay, and therefore the probability of error due to S2 is at most n to the 4 over 2 to the n epsilon. So that vanishes. Okay. All right. I know I'm a little bit over time. If I have 5 minutes, can I go 5 minutes over time? Because I do want to just highlight the challenges in S0, this other type of thing, talk about what can help us resolve it, and then we'll take a break. Okay? All right. Before I do that, any questions about this? Yeah, information overload. well, let me highlight again. So basically, we took James's point of view, right? His point of view was this oracle given set. He did this action. Bob could be in any one of these balls, and luckily, not too many balls are being confused, and within that, there isn't too much intersection between them. So you can basically figure out, okay, only a very small fraction of this blob is bad. Most of this blob is good. So it doesn't matter what the S vector is. This will always be true. Union bound over all S, Z, blah, blah, blah. Okay, that works out. Now, the challenge is, what happens with the S0 type of, S1 is similar, I'm really not going to bother. With S0, the problem is the following. So S0, remember, was what is the probability that within this blob, there'll be a code word also within the oracle given set. Okay? And this is more challenging to characterize because if you think about it, over here, the error events are correlated, right? Because you're translating, so you start off with code words in the oracle given set, you translate by S, and then you ask what is the probability that there's another code word within that oracle given set that falls within that blob. So these are correlated events, which makes it tricky to analyze directly. Okay? But a simple trick actually, so that's a problem, but the resolution turns out to be not too bad, and it just turns out to be a trick really. Okay? So the trick is, you take your 2 to the epsilon n code words, you partition them, and this is just mentally, there's no actual partition happening in your actual code book or anything like that. Just mentally you partition them into a grid of, with 2 to the n epsilon by 2, 2 to the n epsilon by 2, something like this. So write them like this. And then compute our error events like this, and then like this, by which I mean the following. What is the probability that, let's say, these are the code words in one particular column. So these 3 crosses correspond to one column. So given this column, what is the probability that anything outside this column is going to confuse it? Okay? So now the code words outside this column, it's like these remaining code words are like S2 for this column. Okay? So compute that error event, turns out to be small. Do it for every single column and every single row. Take the union bound, and you can convince yourself that really, if something is going to cause an error event, it has to be confused by something either in a different column or in a different row. Because if something is in the same column and the same row, then it's that same event, right? You can't be confused by yourself. So really, it's just the silly little trick of partitioning your space into an appropriate number of subsets, and then taking a union bound over all of these, and that helps you deal with this more special case as well. So this is what I call reverse list decoding, and it gives you something. Okay? And there's a fair bit more coming up. You can see from the slide number. Let me just see if I want to highlight anything. Okay, let's take a break, but let me leave at the bottom the fact that this can be generalized quite a lot to a whole bunch of other channels and so on. But I'll just leave it at the slide, and let's take I think 25-minute break or thereabouts. Yeah. All right.